Thank you. So yeah, some of you might recognize me from earlier, but now I'm going to talk about my sort of actual work, which is on MANTID imaging. So this is a project at ISIS, sort of related to the MANTID project, but it's a separate code base. And I've listed the developers within the team, some current, some previous, and a few of them are in the room here somewhere. Hello. So let's start at the beginning. What is neutron imaging? So this is where, so we work with the IMAT experiment at ISIS. This is our imaging beamline. And the basic idea is you take a beam of neutrons, you pass it through the sample that you're interested in, and then you have a pixel detector behind. So you're not doing diffraction, you're just looking at effectively the shadow. So it's like a medical X-ray. So from that you get, so you can put your object in, you get projections. So these, you can kind of see what the object is. These are the sort of shadow images from the attenuation of the neutrons. The next thing you can do is reconstruction, where you take a series of those projections from a rotated object and turn that into a 3D model. And this has lots of applications in engineering, in paleontology and archaeology, in plant sciences, all sorts of things. So the process of going from those projections into a 3D volume is called tomography. So we typically take a set of projections which arrive to us as TIFFs or sometimes in the Nexus file. We also have some extra things like flat and dark, the 180-degree projection that makes some of the alignment easier. And we might typically have about 20 gigabytes of this raw projection data. We then go through this process called tomography, and this takes all those projections at different angles and calculates what must be the attenuation at each voxel in the volume in order to give you those projections. So this is called back projection, and there's quite a few algorithms for doing this. But yeah, the key thing to understand is that at the top here, where you see P, that's a projection. So that's a shadow image that has everything flattened down into a single plane. Once you've done your reconstruction, you can take slices out, so you can see things in front of things and behind things and see exactly what you want. Our software uses a few different algorithms. So filter back projection is the kind of most commonly used method. We also support some iterative techniques, and one of these is quite an advanced regularized iterative technique called TVPDHG, and that has a good resilience to noise, though it's quite CPU or GPU intensive. We also have a grid rec, which is from Tomopy, which doesn't need a GPU, so we can also support this on a machine that doesn't have a GPU. So MANTID imaging, this is our user-friendly interface for doing this work. So we start from the images that come from the experiments. These usually require some pre-processing. So to do flat fielding, noise reduction, cropping, things like that. And then we have the tools for reconstruction. And just to be clear, we don't share any code with MANTID. We're a separate repository for that. There's overlap in developers, especially over time. So one of the things that I think makes MANTID imaging stand out is that it has this high performance user interface that really lets you move around and look at your data and zoom in and explore and spin and adjust levels very quickly and easily. And that means the users can really get a feel for what they're looking at. We have a selection of pre-processing tools. So this is just showing an outlier removal. I don't know if it shows up very well, but there's some spots in the first image and they've been removed in the second. And then we have our reconstruction GUI that lets you look at slices and adjust your parameters and see a live preview. So the development team, we have approximately 3 core developers currently. It's shuffling around a little bit, and then we've had various previous developers who've worked on it. Our most recent release was 2.4, which was in September, and we run on Windows or Linux, and we deploy mostly to our users using IDaaS, which is the ISIS data analysis as a service. We build on lots of existing tools, so there's lots of great libraries for doing the difficult algorithmic part of this work. So for example, ASTRA Toolbox and the core imaging library from the CCPI project. So we're using those libraries, so we get the best cutting edge technology for actually doing these reconstructions. And we have an agile development method. We try and be as test driven as we can. Continuous integration, we're open source, and we have a good relationship with the users. So we have every fortnight a meeting with the Beamline scientists on IMAT, and we have fairly regular releases. In terms of history, it's a fairly new project, but it goes back a bit further in history. So there was initially some work that was part of MANTID, and then after that it got extracted out and became its own project. In 2019, the effort really picked up because IMAT was using a piece of software called Octopus, and that was going end of life. So there was an urgency to have something that could replace that. So our first kind of end user release ended up being called 2.0. That came out around the start of 2021. And since then we've done several point releases, and you can see that it's visually changed quite a lot over that time. So more recently, since our first user release, we've done lots of work on improving the user interface, improving usability, and adding new features, so these more advanced reconstruction algorithms, and then just tools to make things easier. So a recent one was having a line profile when you're previewing your reconstruction. So it's just, we work on basically what IMAT prioritizes and what they need. We're also beginning to look at energy resolved imaging. So we have an initial spectrum viewer in the most recent release. So this is just one of the recent features, and it kind of, I think, is a good example of why having graphical software can be good. Obviously, it's not what you want for everything, but allowing your data to really see, allowing the users to really see what their data is, what they have, what problems there might be with it. So this data set at the top has the issue where the soil region in this sample has a very high attenuation, and there's a slight mismatch with the dark frame. That means when you do the subtraction, you actually get some negative values in some of your pixels. A negative value, if you interpret it physically, means that you have negative attenuation and more neutrons arrived at a pixel than were in the beam. So it doesn't really make sense. If you put that into a reconstruction algorithm, you get generally pretty weird results because it's non-physical. So it was important to make it clear to the user, why that was happening, what they could do to fix it. We did initially think maybe this is something we can just solve automatically. If it's negative, we increase it to 0, just clamp it. But through discussion with the users, they wanted really to know what was wrong and understand how they could fix it. I'm going to put a sustainability slide in. I think everyone should have a sustainability slide. So these are some kind of things that we've been doing, not necessarily entirely for sustainability reasons, you know, the requirements do feed into that. So one of them is these new advanced reconstruction algorithms. And because they're more robust to noise and robust to having a reduced set of projection angles, that opens up maybe the possibility of running the actual experiments faster, taking less projections, and being able to work with not quite so perfect data sets. Something that ties into that is golden angle scanning. So this is quite a nice technique. So normally, or what's currently done is you decide how many angles you want. So you might want to do 1,000 angles. So you divide your 360 by 1,000 and you set up your machine to step through all of those. That has the issue that you can't stop halfway because you've only sampled part of your arc. So golden angle is about, so this relates to the golden ratio. This is an angle which, if you step by that much each time, no matter when you stop, you have a good spread of angles around 360 degrees. It's not a new idea. Plants have been doing it with positioning their leaves for a long time. So you can find this in quite a lot of plants. The leaf will be offset from the previous leaf by approximately this angle or some factor of it. So you end up with quite a good spread so that leaves don't cast shadows in the leaves below. And then another thing we've been doing is improving the testing and benchmarking. So hopefully in the next release, we'll put some work into optimizing and improving performance a bit. The future, so one of the things that we want to be able to do is energy resolved imaging and energy resolved tomography. So there's quite a few options for exactly what this could mean. The basic idea to it is you record the time of arrival of your neutrons. So you start going into event mode. And by that time of arrival, you can work out what the energy of that particular neutron was. And you can then, for each pixel now becomes a spectrum rather than just a count. This means you have a big increase of data, but it depends exactly what your reduction workflow is. So you might decide that you actually just want to look at a few specific windows within that data, or you might be able to compress down to a scalar value based on maybe a Bragg edge, position of a Bragg edge. So we're looking at this, currently looking at how we read some of these file formats and how we integrate this into the software. And this, the spectrum viewer was the kind of first step along that road. And then there's various other things that the scientists are interested in setting. So in summary, this is a user-friendly GUI. This should be something that most users can sit at and have a fairly intuitive use of. We have some documentations and walkthroughs and a basic wizard to help users. It's being used already at IMAT, at ISIS, and we'd like to hear from people at other institutes using it. There's nothing IMAT specific in there, but I'm sure when people have slightly different file formats and directory structures, that there may be things that we need to look at. So if you want to give it a go, then get in contact if you find any issues. We have a good range of tools. Again, it's not specific to neutrons, but we probably don't have the pre-processing tools that you'd want for doing X-ray tomography. If someone is interested in that, come and chat, and we'd be happy to collaborate. And it's an agile project, so we're really driven by what the users want. If you're interested, there's the GitHub link, there's a DOI and rather long support email, but you don't copy it down, you can find it through those links. Thank you. Any questions?
So there's 5 more questions. Do you have any feature or try to work with a racing patient or when the sample is moving and you have velocity? do it?
So the question is whether we do, I guess, any sort of dynamic tomography.
Yes.
We don't currently, so this is, yeah, we currently consider three-dimensional data, so your projections in X, Y, and then angles. So adding another dimension for time would be an interesting thing, but yeah, that's the future project. The samples we work with are mostly small static objects. Yeah.
I've seen your project is hosted on GitHub and that you are using FAR, and that you said that you are doing continuous integration. I was wondering on which kind of hardware and how do you perform continuous integration with hardware or with software that requires GPUs? So
this is, do we use, how do we do our continuous integration given that the GitHub actions don't have GPUs? The answer is that we don't for those bits of the code at the moment. So that's why, one of the reasons why we want to have a CPU capable reconstruction algorithm in there. But yeah, we're looking at maybe using work of our own workers that then talk to that system. Yeah.
If there's any other questions, please post it on Slack and we can take it from there. Thanks, speaker again.
Thank you.